Okay, so today's topic is, well, it's numerical integration. You may not know what that is, but we'll find out. And let's talk about, first of all, why we would need it. So what if we wanted to find the area enclosed by this graph? It's not a function, right? Violates vertical line test. Uh, but what could I do maybe to find that complete area? And I've given you a hint, because look, there's a shaded area. That times 4, right? Okay, so how could I set up that integral that represents that shaded area? What would I have to do to this relation? Yeah, I solve for y, right? If I solve for y, I would just get y squared equals 1 minus x to the fourth. So y equals plus or minus the square root of 1 minus x to the fourth. The top function would be, this is going to be y equals positive square root of 1 minus x to the fourth. And the bottom function down there would be y equals negative the square root of 1 minus x to the fourth. Separately, those are functions, right? So we could integrate that. That's just going to end up being that integral, right? Everybody good? Okay. So we can do that in Desmos, and that's what it tells me. It gives me an answer, right? Okay, but what if we don't have access to Desmos? What if we want to find this analytically? Could we find a way to do this integral with some tricky technique? And the answer is no, you can't do it. That's an impossible integral to do. The exact area cannot be found at all. You can't find it anyway, but calculus would be the way that we could, but we can't. It's not an integrable function, okay? That square, the integrand is not a function that can be integrated. There is no antiderivative that exists in the universe whose derivative is that. It's impossible. Strange that kind of thing happens, but it does. But clearly, this is a bounded area, and we should be able to find it, right? Well, this is one of those situations in math where sadly we can't find an exact answer. We have to use numerical methods. So we have to approximate the area. Yep.
Wait, so that blue function, there's nothing, like you can't grab anything that
No.
represents.
No, there's no way to do it. Now you could build you could build like a Fourier function that would closely mimic that function if you wanted to, but that's a lot of work. Or we could do some stuff we already know how to do, right? We can't find, I mean, it's weird that it's that way, but there are some relatively simple equations that you can't integrate, believe it or not. I mean, it's like there's some of them that don't seem like they'd be that big a deal, like this one, right? That seems like we ought to be able to integrate that some way if we use some kind of a trick, right? Use substitution or integrating some stuff you guys haven't learned yet, integrating by parts or a trig substitution, or it doesn't matter how hard you work at it, you're never going to get it. It's just there is no elementary function whose derivative is that. So we have to settle for an approximation, right? Well, what are some ways that we could approximate that orange area? You already have one way you could do it. How could we do it? We've done some stuff like this in the past where we approximated areas under curves, didn't we? How did we do that? Yeah, we used a sum of rectangles, right? We could do that. We could cut this thing into a bunch of rectangles, but what we couldn't do is we could not let the number of rectangles approach infinity. That limit wouldn't exist, or we could integrate this thing. So we can't take the limit, but we could just set a really large number of rectangles to get an accurate approximation, right? Okay, rectangles are not the most efficient way of doing this though, because rectangles don't match that curve super well, do they? They have flat tops on them. and flat tops aren't going to match the parts of the curve that aren't horizontal, right? That have steep slopes. So rectangles, maybe we could improve on that idea a little bit. Well, one thing we could do is we could use rectangles built from the midpoints of each subinterval. Okay, this is called the midpoint rule. So let's just, I mean, this is something I don't even think necessarily, I don't know if this is, one source says it is and one source says it isn't. I don't know if this is even on the AP test, honestly, but it's pretty easy to do. And the kinds of problems you would see on the AP test are not difficult. They're going to be a relatively small number of shapes that you're going to add up, small number of intervals, right? Subintervals that you're going to add up, slices we called it, right? So what's the midpoint rule then? Well, the midpoint rule just says if I want to approximate the area under a curve using the midpoints of each subinterval to define the height, which makes sense, doesn't it? Because the midpoint is going to be a pretty good approximation, right? If I go back and look at this picture, you know, we can see that if I were going to draw a left sum, and let's just say this is the ith subinterval, well, the left sum would be too big, right? It would overshoot a little bit, wouldn't it? No, it undershoot, sorry. It'd undershoot a little bit, wouldn't it? Because it's a decreasing function, and so I meant right. That's a right sum, right? The right sum would undershoot because the right edge of that subinterval is going to be the height of the function, and to the left of that, that's going to be less than the function. Everybody agree that if I added all those up, it would undershoot the area a little bit, under approximate? Well, if I instead did a left sum, that's going to overshoot a little bit, right? And so if we take the midpoint, that ought to be pretty close to averaging that out. It's not going to be exact because the curve isn't flat on top. It's not linear, and so it's not going to be a perfectly down the middle of those two errors, right? It's going to be still off by a tiny bit, but it's going to be much closer than the rectangles defined by the left or the right edge. The rectangles defined by the midpoint will be a better approximation. So here's our formula for doing that. It's no big deal, right? What does this mean? Well, we're adding up all these rectangles. Don't they all just have a width times a height, right? What's the width of each rectangle? It's delta x, which is just b minus a over n, right? So if I distributed this to each one of those terms, that's just going to be the width of each rectangle. The height is going to be given by the value of the function at the midpoint. And that's how we define the midpoint. When you put a bar over a quantity, it means average in math, right? So x1 bar, what's that mean? X1 bar just means the average value of the x's in the first subinterval. So you're just going to average the x value of the left and right edges of that subinterval. So if we take the ith subinterval, x sub I bar is just going to be, what is it? What's the average of whatever x sub I minus 1 is and whatever x sub I is, right? So on that interval that starts at x sub I minus 1 and ends at x sub I, that's halfway between those two x values. We average the endpoints of that subinterval, and it gives us the midpoint, right? That's all a midpoint is an average between the beginning and the end of an interval, okay? And what is, let's remind ourselves, what is x sub I? Well, x sub I is always just going to be the starting place for our interval, a plus I times delta x. Delta x is b minus a over n, right? How do we get to x sub I? We start at the beginning of our interval, and we take I steps of width delta x to get to the right edge, right? X sub I just means the right edge of the ith subinterval, right? Is this all, remember all this stuff? This all kind of making sense, right? I mean, we did this a while ago, right? But this is the stuff leading into definite integrals. Remember we talked about how to do all these Riemann sums. Okay, so anyway, the point is it's a pretty simple formula, right? It's just delta x times the sum of the midpoints. Okay, so if we're doing a problem like something like this, where I'm only using 4 subintervals, and I want to use the midpoint rule, that's easy, right? I just have to figure out there's only 4 subintervals. I just have to figure out what are the x values of the midpoints of each of those slices, okay? So if I'm trying to approximate the area under this function from 1 to 2, and I'm using 4 subintervals, what is delta x, the width of each subinterval, going to be? My area goes from 1 to 2. I'm adding up the area under the curve from x equals 1 to x equals 2. So what's the width of my interval? 1. And I'm dividing it into 4 equal subintervals. So what's the width of each one? 1/4, right? All it is just b minus a, 2 minus 1 divided by 4, right? So it's 1/4. So what would my grid points be that are going to bracket each subinterval? Well, the start, a is equal to 1, right? Oops. So the left edge of the first subinterval is just 1. What's the right edge of the first subinterval? You just told me that the width of each subinterval is 1/4. Yeah, so 5/4, right? So that's the right edge of the first subinterval, and what else would it be? Left edge of the next one, left edge of the second subinterval, right? What's the right edge of the second subinterval? 6/4, which would just be 3/2, right? Okay. Next grid spot would just be what, 7/4, and then finally 2. Everybody see that? So my first subinterval, like if I want to kind of keep track of where the subintervals are, the first subinterval just goes from there to there. The second one's going to go from there to there. Third one goes from there to there. And the fourth one, whoops, goes from there to there, right? So if I want the midpoints of each of those, well, what's the midpoint of the first one? What's halfway between 1 and 5/4? 9/8, right? Between 8/8 and 10/8 would be 9/8. What's the midpoint of the second one? Yeah, 11/8, right? Because we're going between 10/8 and 12/8, right? It would be 11/8. And they're just going, obviously these are just going up by 2/8, aren't they, right? The midpoints are all going to be 1/4 apart. So these would be the values of the midpoints. So those are the values I would just plug in. This is no big deal, right? If I want to calculate this, the midpoint approximation here, it's just going to be 1/4, that's delta x, times f of 9/8 plus f of 11/8 plus f of 13/8 plus f of 15/8. Done. Just plug those into the function, and we get an answer, right? Question? It's the average x bar. Just means it's the midpoint of that interval, of the ith subinterval. So x sub I bar is going to be x sub I minus 1. That's just, and let's make a note here. That's just the left edge of the ith subinterval. Right? That's that guy. And then x sub I is the right edge. Oops, can't spell. Right? So we're just going to average those two, add them up and divide by 2. Yep.
Why are we like doing all the work to get the midpoint when you said that they're both going to go to the same thing if you just did like the right sum?
They're not, though, because we can't take a limit of these. The function's not integrable. So we can't, no, if we could take a limit, we could do the integral. So you can't take a limit as n approaches infinity. It's going to be a limit that's you can't resolve, you can't evaluate, okay? So you have to settle for just a big number. So you want to pick an efficient shape. You don't want to pick a right sum or a left sum. You want to use a midpoint sum because it's way, way more efficient, right? Does that make sense? The right sum is going to always be off by a fair amount. The left sum is going to be off by a fair amount. The midpoint sum is going to be pretty close. It's going to average those two is really what it is, right? Okay. So that's no big deal, right? We can, if we have a small number of subintervals, which you always will on the AP test, you just do it manually like that, okay? But I want to show you there's more to life than the AP test, and I want to show you how you could do this for really big numbers, right? Use technology, and that's important to be able to do. So what could we do here? Well, we could, instead of adding up a finite number, let's make this number potentially really big and use sigma notation, right? So what is the definition? We're just going to sum up f of x sub I as I goes from 1 to n, right? So what is f of x sub I? Well, it's just x sub I minus 1, which is just this stuff, right? That's just that stuff right there, isn't it? Right? X sub I minus 1 is just a plus I minus 1 delta x. Well, there's delta x, b minus a over n, right? Plus x sub I, well, that's just that stuff right there, divided by 2, right? And if I just work inside those, inside the argument of that function there, if I just, if I were to just combine like terms here, what you're going to get is that, right? You're going to add this stuff up and you're going to get a plus a is 2a. If I get I minus 1 times b minus a plus I times b minus a, well, that's b minus a times I minus 1 plus I, 2i minus 1, right? So I just derived, this isn't in the books or anything, but I always like to present this as a simple formula. So this is just, it's easy to do, just derived a simple formula for the midpoint rule that is completely general, right? That's going to work every time for the midpoint formula. The specifics are just going to be what are a and b, the limits of integration, and what's the function, right? What's the function f of x? Oh, and then n. How many rectangles are you making, right? You plug in those parameters based on what problem you're solving, but that otherwise that's completely general, right? So how could we apply that? Like that would be something, if we were going to do a similar problem to the one we just did, but with 50 subintervals, well, you're not going to add up 50 subintervals, right? You don't want to calculate 50 midpoints and add those up manually. That's ridiculous. So we would use the sigma notation form then, right? So what's this going to look like then? So if we're going to try to add this thing up, I can't even remember. Oh yeah, so what goes out front then? What's delta x? B minus a over n for this problem with 50 subintervals. Say it again. 1/50th, yeah. 2 minus 1 over 50, right? So I get 1/50th is delta x. That's the constant that sits out in front of the sigma. And we're just going to add this up from 1 to 50, right? Because we have 50 subintervals. Well, what's going to show up in here then? I'm going to get 2 times a. That's just going to be a 2, right? Plus 2i minus 1 times b minus a. Well, that's just 1, right? B minus a is just 1 divided by n over 2. Okay, good. So all that stuff really just simplifies to that. And now let's plug in what the actual function is. Well, f of hand is e to the hand divided by hand. Well, there's e to the hand divided by hand, right? Now I would just plug that into, a technology to sum that for me. And if I do that, I get that answer, which is more accurate than that answer, right? With 4 midpoints, that's what we got. With 50, that's what we got. So we improved. Okay, make sense?
What was the one, or is this the same problem as the one before?
It is. It's exactly the same problem. We just used 50 subintervals.
No, like the page.
Let me go. I don't remember what page 4 was. I lost track. What was that one? Oh, that was different. Yeah. Yeah, that was different. We never actually did that problem. Yeah. Yeah, I mean, we could, right? That's so that's how, that's an application of AP style where you're just adding up. The most they'll have you add up, I think, is 8. And even that would be, I don't think they'll even have you add up 8, right? So those are all numbers that you could do just manually. You don't have to use a discrete sum using sigma notation or anything, right? But it's easy to do. If you want a big number of subintervals and you want a very accurate area, that's a way you could do it, okay? All right, so that's the midpoint rule. The rule that generally people prefer to use is called the trapezoidal rule, which is where we're going to take a different approach. Instead of adding up midpoints of subintervals, we're just going to, rectangles, instead of using rectangles defined by the midpoint, where the height is defined by the midpoint of each subinterval, instead, let's just use a shape that's going to match the function better, which would be like a trapezoid, right? If we carve this thing up into trapezoids, well, the trapezoids have sloped ceilings on them, right? That match kind of the average slope of the function over that interval, okay? You see how that would be an improvement? The next step would be to use Simpson's rule, which I'll show you what the formula is, but that's the BC test doesn't even go into Simpson's rule. So, although I always taught that in the past. If we had a little more time, we'll come back and look at that later. There's an interesting discussion you can have about this, which is when you're doing numerical methods like this, which is what technology does. Technology, unless it's a authentic computer algebra system, technology really doesn't do symbolic math. It just does numerical analysis, like your TI-84s or Desmos. They don't do symbolic math. They do something where they're going to use an algorithm to estimate an area, right? So an interesting question pops up: which algorithm do you use? What we're going to find is, like with trapezoids, they don't match the curvature on the top because they have a linear ceiling on them. Simpson's rule has a quadratic ceiling, so it's going to do like a best fit parabola to fit the curve on the top of each what used to be a trapezoid. They're like trapezoids with parabolic tops on them to better match the curve. Okay, as you're going to see, Simpson's rule, though, it's a tougher algorithm. I mean, there's more calculations to do to calculate Simpson's rule, okay? So, especially if you're including like error estimates in this, which you'd need to do, you'd need to get it to a certain accuracy, right? And so what you'd have to do if you were a computer scientist and you were trying to design the software and the hardware to make these kinds of numerical approximations quickly, you've got to kind of figure out, okay, what's going to make more sense here? Do I do a simple algorithm like trapezoidal rule with a large number of large number of subintervals, right? Which would mean you're going to do lots of computations, but smaller computations, or do you do less subintervals using Simpson's rule, which requires much heavier computation for each calculation? And there's a fine line there. There's a fine line. It's processors typically, like our really fast processors now, typically just do lots of simple operations very, very fast, right? But as we get into more advanced computer design, the next step is already starting to be parallel processing, which is what our brain does, where you can have relatively slow processing speeds, but you can do multiple threads in parallel. And as we're able to do stuff like that, we'll be able to do much more difficult calculations in parallel, and it's going to shift things to where we're going to instead be able to do more complicated algorithms with fewer iterations, right? Lower processing speed. And that means that you have the heat requirements ultimately become a big deal, right? How you have to put things so close together so you're minimizing the amount of heat. Well, there's a whole physics, thermodynamic component that goes into this, right? Where the biggest problem that computers have now is dissipating heat. And this is going to be that way into the future, right? We're limited by the amount of heat that you can evacuate out of the computer to keep it working. It only functions within a certain environmental range, of temperatures. And so anyway, we could talk about this for days. But anyway, there's interesting conversations you can have about this stuff, right, that are more theoretical. Okay, what about the trapezoidal rule? Let's get down to nuts and bolts here. So let's review, what is a trapezoid? Well, you guys remember trapezoids, right? Trapezoids are quadrilaterals with exactly one pair of parallel sides and one pair of non-parallel sides, right? So we'd say that the two parallel sides we call I think we called those bases. Yeah, B1 and B2. And then the height is the distance between those bases. Well, if you want to add up the area of a trapezoid, the easiest way to do it would just be to do something like this, right? We would just cut this trapezoid into pieces, where I'm going to take this piece and I'm going to flip it around and put it there, right? I'm going to cut this piece at its midpoint and I'm going to flip it around and put it there. Well, what did we accomplish? We built a rectangle where the width of the rectangle is h, and the height would be the average of the two bases, wouldn't it? Right? Because in order to make this work, didn't I cut these two segments, these two sides, right at their midpoints? So those distances are always going to be equal, right? So the bottom, the larger base is going to shrink by the same amount that the upper base grows. And so we meet at an average, don't we? Right? You can just kind of see that geometrically. That's the way it has to work. Yes, sir. No, it's not, because we're not actually using rectangles. We're using trapezoids. Okay. It is. You know, I think these give us different. Why do they give us different values? Oh, they do, because I think the midpoint rule is actually better. Because the midpoint rule, they're not the same. Because the height of the function, the trapezoid assumes that the function is linearly transitioning between the left edge and the right edge. The midpoint rule doesn't do that. It takes the value of the function at the midpoint and calculates the height of the rectangle that way. See what I'm saying? So a function that curves, the midpoint rule is going to be a little bit more accurate, because it's going to place, you get what I'm saying? Like if this thing's curving up, the midpoint of this interval is not going to be, it's not going to intersect with the secant line connecting those 2 points, right? You get my point? So here's it's a good question. I want to answer it. Those look pretty similar, but if I were to focus in, I would see that in this case, the red top of the function is going to be slightly below the blue secant line, because this is a concave up function, right? You see my point? And so the trapezoidal rule assumes that the height of the rectangle is the midpoint of the blue segment. The midpoint rule takes the midpoint of the actual function to define the height of the rectangle, right? Okay, which is better? Probably the height of the function, right? Because it's going to be, as it curves up, you're going to get, well, we don't need to launch into too much of this. I mean, you can just think about that and figure out why that's better. It'd be a little bit better. Yeah. Okay, so anyway, but trapezoidal rule we'll see is easier to calculate. Okay. So then what do we got here? I forget what I even did here. Let's see what I have. So there's the area of a trapezoid, right? It's average of the bases over the height, or times the height. And our trapezoids are going to look specifically more like that, right? They're going to have a horizontal base and the top of the trapezoid. The bases are now the vertical edges, right, that define the heights of each side of the trapezoid. And the top of the trapezoid is the one that's going to be custom fit to match as well as possible the curvature of the function, right? Okay. How do we set this up then? Well, if we want to add up these areas, the area by the trapezoid rule, it's just going to be this, right? It's going to be, we'll make the width of each trapezoid the same. It's just going to be, let's see here. How did I get that? Oh, never mind. I see what I'm doing. Okay. Yeah, this is what the individual trapezoids would look like, right? If I were to add these things up. The first trapezoid is just going to be the height, the left edge, call it B1, is just going to be the value of the function at x sub 0. Whoops. The right edge is going to be the value at x sub 1. And we're just calculating this trapezoid, aren't we? Right there, that area. The width is going to be delta x, right? So we average the two bases of the trapezoid and multiply that by the width, and it gives us the area of the first trapezoid. The second one is just going to be this guy right there, right? Left base becomes x sub 1, right base becomes x sub 2, and so on. We just add that up for every trapezoid that we're using. Okay, make sense? Okay, keep in mind also, remember I did, oh, I see what I did there. Well, that's tricky. Okay, I outsmart myself here a little bit sometimes. I can't remember what I did to make these flip charts. So we add that all the way up. The very last two trapezoids would be that one and that one, right? So that's x sub n minus 2 is the left base. X sub n minus 1 is the right base. And the very last one would be x sub n minus 1 and x sub n. Okay? Okay, well, that's not going to be a very convenient way to do it for a large number of trapezoids. So we have to figure out a way to sum this stuff. Okay, well, let's factor out a delta x from each of those. What is that doing? Man, I don't know what I got going here. What is that thing for? I don't know. Okay. Oh, that gets rid of that guy. Okay, right. So we factor out a delta x, and we could factor out a 1/2, right? Because each one of those terms is divided by 2, isn't it? So what am I left with then? Well, if I factor out the delta x and the 1/2, I've just got f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2. What do you notice? If I do that all the way through, look at what our sum looks like. Do you see anything peculiar about that? Okay, every single one is double counted except which ones? The end ones, right? Because each of the intermediate ones, like x sub 1 is going to serve as the right edge of the first subinterval and the left edge of the second subinterval. But x sub 0, or a, is only ever a left edge one time. It's never a right edge. And x sub n, or b, same thing, is only a right edge one time. It's never a left edge, right? So those ones don't get double counted. So then we could divide this up kind of like that, right? All of these are double counted and those aren't. So when I want to sum this up, I could take these two individual pieces and add those, find those heights and add those individually. But everything in between A and B, all of those grid points, I'm going to add those up times 2. The value of the function at each of those places times 2. They're double counted. So we can just do something, we can just do something like that, right? I can combine like terms and I get 2 of those plus 2 of those plus 2 of those, all, and then just factor a 2 out, okay? And look what that gives us. That just gives us something like that, right? Delta x is b minus a over n times 1/2 is b minus a over 2n. So that's going to be the constant that sits out in front of our sum. And then we're just going to add up, we're going to multiply that times the value of the function at a plus the value of the function at b plus 2 times the value of the function at x sub I. But I is only going to go from 1 to n minus 1, right? Because it's only, only these terms that stop at n minus 1 and start at x sub 1 are double counted. So I call that the interior sum. So the trapezoidal rule is just this: b minus a over 2n times the quantity f of a plus f of b plus 2 times the interior sum. Okay? So if we want to add this, if we want to actually use this rule then, like if I want to calculate the area under a curve for n equals 8, we'll just add it up manually. It's no big deal, right? We would just go b minus a over 2n. Well, that's 2 pi minus 0 over 2 times 8 is 16, so 2 pi over 16 sits out front. Then I've got f of 0, so sine of 0 plus f of 2 pi, so that's plus sine of 2 pi, plus 2 times the value of the function at each of the other grid points, right? Well, if we're going from 0 to 2 pi and n equals 8, then what is delta x? Delta x would just be 2 pi over 8, right? B minus a over n, which is just pi over 4, okay? So then I'm just going to add to this 2 times the quantity sine of pi fourths plus sine of 2/4 pi plus sine of 3/4 pi plus sine of 4/4 pi, etc., all the way up to 7/4 pi. Okay, yep.
So, right out from the integral sine x dx,
Yeah,
that's not the approximating?
this is approximating it. This is one we could do, right? But we're just approximating it with the trapezoidal rule for n equals 8. So 8 trapezoids would give us this result. I think did I just delete it or something? I think I did that. There we go. Oh, I did delete it, didn't I? What the heck? Oh, there it is. Okay, so I got to go forward a little bit. There. Okay, so if we just plug that stuff in, that's what I get. Okay? Negative 8.72 times 10 to the negative 17. That's a pretty good approximation of 0, right? Using the trapezoidal rule. You don't need a huge number of trapezoids in some cases to get a pretty accurate answer. And you could do this down here. Like if I wanted to, instead of adding those up individually, I could have just done that too, right? I could have just said, the interior sum is just going to be the sum of f of x sub I from 1 to n minus 1. Well, what's f of x sub I? X sub I, remember, is always just equal to a plus I delta x. So it would be 0 plus I times pi fourths. Well, the sign of 0 plus I times pi fourths. There's x sub I right there. As I goes from 1 to 7. So I could even do that just using sigma notation if I want to, right? Or I could add it up individually. Either way, I'm going to get that. Okay, but what happens if I want to add up a really big number of trapezoids, like 100? Then I definitely want to use my sigma definition, right? So this is slightly different this time. This time we get A is pi, B is 2 pi, N is 100. So delta x is going to be pi over 100, right? 2 pi minus pi over 100. And x sub I in this case is going to be pi plus I delta x, I pi over 100, right? So when I add this thing up then, I'm just going to plug and chug, right? Out front I get b minus a over 2n, so I get pi over 200 times f of a plus f of b. So sine, I start at the endpoints, sine of pi plus sine of 2 pi plus 2 times the interior sum. The sine of x sub I as I goes from 1 to 99. 2 times that sum though, because I'm double counting each of those, right? And if I just plug all that stuff in, I get that. Yep. Say it again.
A is x sub 0?
Yes, right. X sub 0 is A and X sub n is B. Yep. Okay, good. So those are applications. So in our text, they define the trapezoidal rule as the average of the left and right Riemann sums. You can do it this way too. I just have never taught it this way, but you can do it this way too if you want to, right? That would make the algorithm a little different. It's just b minus a over n then, the width of each subinterval times the average of the left and right Riemann sums. So I would just sum the left Riemann sum plus the sum of the right Riemann sum all over 2. That works. That would give us something like that, okay? if we do the same problem. Actually, see, look how much more accurate this is. If we only use 50 subintervals, oh, that's same, never mind, that's the same thing. Never mind, what am I saying? It's trapezoidal rule, same answer. Okay, the other part that we're not going to get into, this is not on the AP exam, we'll come back to this. If the function has a continuous second derivative, then there is an error formula for approximating the error in the trapezoidal rule, which is really interesting. This is how you find it, using this formula. The maximum error, the absolute value of the error, is less than or equal to this expression, guaranteed. What is this? B minus A cubed over 12n squared. I'm not going to derive this for you. It just takes too long, and it's not really germane to what we're doing. I mean, we'll come back and maybe apply this at the very end of the year. But you're going to multiply that ratio times the maximum of the absolute value of the second derivative on our interval, okay? That sometimes is tricky to find, but oftentimes it's not. Oftentimes it's pretty easy to figure out where the second derivative is going to have its maximum, because typically the function is going to be monotonic increasing or decreasing on that interval. And so it's not hard to do. But you just plug stuff into that and it gives you an answer. Like, for example, when are we out of here? 1 minute? Okay, I'll stop here then. But this is something you don't need to know this, right? The assignment, I never have you calculate this on the assignment. All you're going to do is just literally you're going to go through and practice doing some, like, a couple midpoint rule problems, a few trapezoidal rule problems for small numbers of n. And then I programmed a couple problems, so you had to do a couple trapezoidal rule problems with bigger n, just so you have to use sigma notation to get used to that. But that's it. That's all you do on the assignment. This is stuff I want to introduce you to, but we're not going to do anything with it. All right, have a good lunch.